In section 8.2, we introduce the rate distortion function. We first define a rate distortion code. Here, all the discussions are with respect to an IID information source x sub k greater than or equal to 1, with generic random variable x and a distortion measure d. An NM rate distortion code, where n is the block length, is defined by an encoding function f from the source alphabet x to the power n to an index set 1, 2 up to m, and a decoding function g from the index set 1, 2 up to m to the reproduction alphabet x hat to the power n. We will use I to denote the index set 1, 2 up to m. The reproduction sequences G1, G2 up to Gm of length n are called cowords, and the set of all cowords is called the codebook. This is an illustration of a rate distortion code. The source sequence x is fed to the encoder to produce the index f of x. Then the decoder, based on the index f of x, outputs the reproduction sequence x hat. The rate of an NM rate distortion code is 1 over n times log m in bits per symbol. A rate distortion pair RD is asymptotically achievable if for any epsilon greater than 0 there exists for sufficiently large n an NM rate distortion code such that the rate of the code is less than or equal to r plus epsilon, and the probability that the distortion between the source sequence x and the reproduction sequence x hat exceeding d by an amount epsilon is less than or equal to epsilon, where here the reproduction sequence is in fact equal to g of f of x. Here is a remark. If a pair RD is achievable, then R prime D and RD prime are achievable for all R prime greater than or equal to R and D prime greater than or equal to D. This means that if a pair RD is achievable, then R prime D prime are achievable for all R prime greater than or equal to R and D prime greater than or equal to D. The rate distortion region is the set of all achievable pairs RD in the two-dimensional Euclidean space. Theorem 8.12 gives a basic property of the rate distortion region. It says that the rate distortion region is closed and convex. The proof is very simple. First, the closeness follows from the definition of the achievability of an RD pair. Second, the convexity is proved by a technique called time sharing. Specifically, for any mixing coefficient lambda between 0 and 1, we let lambda bar equals 1 minus lambda. If the pair R1D1 and R2D2 are achievable, then so is the pair R lambda D lambda, which is equal to lambda R1 plus lambda bar R2, comma lambda D1 plus lambda bar D2. This can be seen by time sharing between two codes, one achieving RD1 for lambda fraction of the time, and the other one achieving R2D2 for lambda bar fraction of the time. Formally, we need to fix the epsilons and deltas, and the details are given in the textbook. The idea is illustrated in this picture. This is the rate distortion region. Suppose we have a pair R1D1 which is achievable by a certain code, and a pair R2D2 achievable by another code. Now we draw a line to connect the 2 points. The middle point is R1 plus R2 over 2 and d1 plus d2 over 2. Now this pair can be achieved by using the first code for half of the time and the second code for half of the time. Because then, the rate of the resulting code would be the average of R1 and R2, and the distortion of the resulting code would also be the average of D1 and D2. The rate distortion function Rd is the minimum of all rates R for a given distortion D such that Rd is achievable. That is, we fix D and minimize R. On the other hand, the distortion rate function dr is the minimum of all distortions D for a given rate R such that Rd is achievable. That is, we fix R and minimize D. Here are two remarks. First, most of the time we will be using the function R of D instead of the function D of R. Second, if a pair Rd is achievable, then R is greater than or equal to R of D by the definition of R of D. This is an illustration of the rate distortion region, which is convex. If we fix D and minimize R, we get the rate distortion function Rd. On the other hand, if we fix R and minimize D, we get the distortion rates function dr. Theorem 8.15 gives a few basic properties of the rate distortion function Rd. First, Rd is non-increasing in D. Second, Rd is convex. Third, Rd is equal to 0 for D greater than or equal to D max. Fourth, Rd is less than or equal to Hx. The proof goes as follows. For property number 1, let's D prime greater than or equal to D. Then Rd is achievable, implies that Rd prime is also achievable. We have Rd greater than or equal to Rd prime by definition of Rd prime. Therefore, for D prime greater than or equal to D, we have Rd greater than or equal to Rd prime, and hence, Rd is non-increasing in D. The second property, namely that Rd is convex, follows from the convexity of the rate distortion region that we have already proved. For the third property, consider that 0 D max is achievable. By definition of Rd max, we have 0 greater than or equal to Rd max. On the other hand, since Rd max is non-negative, we conclude that Rd max is equal to 0. Therefore, Rd is equal to 0 for D greater than or equal to D max because Rd is non-increasing. This proves property 3. For property 4, since D is assumed to be normal, the pair Hx, 0 is achievable. Because by the source coding theorem, at rate Hx, the source sequence can be reconstructed almost exactly. And if so, because D is normal, the expected distortion can be made arbitrarily small. Therefore, we have Hx greater than or equal to R0, and hence R0 is less than or equal to Hx. This proves property 4. This is an illustration of the Rd curve. Note that Rd is non-increasing and convex. Rd is equal to 0 for D greater than or equal to D max, and R0 is less than or equal to Hx.